Hello, today we're gonna take a look into time token hack, how it was done, and what we can do in order to prevent that from happening ever again. But before starting, I'm Delirious. I'm independent security researcher and dev, performing solo audits, team audits, and bug hunting. So let's dive into this hack. First, in order to understand the core of this attack, we have to go through the ERC 2771, which ironically is called Secure Protocol for Native Meta Transactions. So basically, this is the trusted forwarder. According to EIP, we have like transaction signer, which is the person that does not have to send any transaction by themselves. They just sign the transaction, and there is the other party, the gas relayer, that takes this signature and performs action in the name of the user. So as you can see, it's 2779, so it precedes account abstraction by a lot. Actually, this is like 2020, so a few years back. And you can see here the scope of this ERC. You have this execute function with client address appended, which is a bit fishy. And also you are seeing here this message sender. You may have seen that before, for example, in Open Zeppelin library, the message sender is used quite a lot. So there are some things that the recipient contract that supports trusted forwarder has to do. And most importantly, the second one, extract the transaction signer address from the last 20 bytes of the call data and use it as the original sender of the transaction instead of message sender. I don't know about you, but it looks like a huge security vulnerability for me. And look, like this is official EIP that was actually accepted. And the worst part is if you are seeing in the example here, of course, you are checking if this is trusted forwarder. And if it is, you are taking the signer, which is the message sender, and you are taking last 20 bytes of call data. So maybe let's quickly go through here and see what it really does under the hood. So first, we are subtracting 20 from call data size. This is 20 bytes. Then we are performing call data load, which loads 32 bytes starting from this index, so the last 20 bytes. And finally, we are shifting it right by 96. Okay, so imagine the situation. A whole slot is 32 bytes. Here we are performing call data load of last 20 bytes, but this 20 bytes is padded to the left, so the address looks like similar to this. But we want our address to actually occupy the lowest bytes here, so we are actually shifting it to right. So we are discarding that 12 bytes. Yeah, we are discarding it totally. And now we have our address here by shifting it to right by 96 bits, which is 12 bytes. Cool, but now you can see our message sender is overridden. In case this is trusted forwarder, whatever call data is there and length is longer than 20, we are considering that as trusted forwarder call. And imagine how problematic it might be if this is overridden, and for whatever reason your trusted forwarder can call any arbitrary data to your system. Actually, this is not new vulnerability. Like the first issue with trusted forwarder I found, at least in Solidity, was in 2020 on the audit of pulled together by consensus diligence, and they are mentioning that trusted forwarder undermines the trust assumptions in the system. Yeah, so you can see the message sender is address of price pool, and they are saying here that because of using this, the other persons can impersonate other users. So as I said, this is an old issue. And actually in 2021, 2022, there were many people that were using message sender, like not message.sender, but this structure from OpenZeppelin libraries, and they did not really know what they were doing, but they were actually thinking that maybe if OpenZeppelin supports that, maybe there's, you know, something cool about that, maybe something more gas efficient or anything, you know, because for the most part, everything that comes from OpenZeppelin is like really robust and verified for security. So many people were using that, and OpenZeppelin clearly states you should not use that. At least you have like really good understanding of what you're doing, and usually you are not. So yeah, definitely should not be used. I think that this ERC should never be accepted and should never be done. It is actually one big security vulnerability. Okay, I wanted to show you something very interesting that you may or may not know about Solidity. Solidity only checks if the length of call data that you are putting is at least of this size. It can be longer than that, and Solidity won't really scream on you for that. So I prepared a test here. Simple function. It takes one value, and all it does, it first logs message data, which is the call data that was passed to call to this contract, and logs this value plus 50, so that makes sure that everything works as expected, and any additional call data do not have any effect on this particular function. And I also added fallback because for whatever reason, Remix required me for low-level interactions that fallback is existing, which is a bit strange, but okay, if they need it this way, then I'm okay with that. Okay, so let's say that we have like number 22. Okay, when we put it, we see here, of course, our number 22 is 16 in hexadecimal, and this is how the call data is being shown here. So first 4 bytes are our function selector, which is selector of function test, and to be sure that proper function was called, we can see later 72, which is like 22 plus 50. So now if we take this and copy it here and transact using low-level interactions, all good, right? We have actually the same numbers, the same value. But what now if we will put some additional bytes at the end? So for example, let's give few bytes of ace. When we call transact, you can see here that our call data is now longer. It has additional bytes at the end. However, the value that I put is 22 because I copied it from before, and you can see that this does not interfere with that. So Solidity only takes first 4 bytes as function selector, then it takes whatever it needs to execute this function, and you can see next that all this additional call data that I passed is just discarded. So now look again here, and having this knowledge, I already have goosebumps on my shoulders and on my hands. Just imagine how big of a problem it is if someone is to use that. Because if you are able to actually execute any function as a trusted forwarder and pass some additional data, like the 20 last bytes would be treated as message senders, so you can impersonate anyone. And actually, this is the crux of this hack. I have to mention something about Uniswap. I bet that you know how Uniswap works. We have our X, we have our Y, and of course there is like stable pricing formula, which in case of Uniswap it's X times Y, so liquidity of one token and liquidity of second token multiplied by itself. This is the constant formula. So if you are swapping one token for another, the pool has to be have the same case squared. However, the amount of the tokens from opposite side you will get is smaller and smaller the more you imbalance the pool. This is cool. However, there is one edge case, and actually Uniswap in their white paper are mentioning it, and they are doing actually it. sync function. This is recovery mechanism in case that the token asynchronously deflates the balance of a pair. In this case, trades will receive suboptimal rates, and if no liquidity provider is willing to rectify the situation, the pair is stuck. Sync exists to set the reserves of the contract to current balances, providing somewhat graceful recovery. So when it may happen. So let's say that we have one token that can burn balances, and for whatever reason we are able to impersonate other person and burn all the balances. In this case, the price will be normal because Uniswap really uses underlying reserves for that. So the reserves will stay old and the swap will give unfavorable price. So this is the sync function that when called, it actually syncs the reserves with actual balances of the tokens that it has. And you may already know where this is all going and why I'm talking about this all to you. Now we'll uncover everything and put this together. So this is actual transaction that took place. First, a user is approving time token, deposits ETH to WEF, and swap the token. This is wrapped Ethereum, and the other one is time token. Okay, so the user is swapping 5 wrapped Ethereum, and he wants to get back the time tokens, and minimum amount that he wants to take is 0. Next, we are performing the swap on Uniswap, and finally we are calling the forwarder. So let's see what is this. You can see minimal forwarder for GSN, which is gas station network v2, and you can see here that this is function execute, forward request and signature. Okay, so what it does, it takes the request that user wants to send. In this case, this is from address to address, value, gas limit, nonce, and call data that the user wants to send in these requests, and his signature. So all this that is done in this function, in this trusted forwarder, is you are first verifying that this request is actually being signed by the from address. That means that this person really wants to send it. Then we take from our request the to, and we are performing call here. And you can see here interesting thing. So we take the call data and we append to it from. So this is what the EIP says. If this is trusted forwarder, then take the call data, take last 20 bytes of it, and this is your message sender. Everything according to the EIP. But now, if you go to the time token implementation, you can see that time token also supports multi-call upgradable. And in this case, we have this function multi-call. So what multi-call does is it takes the array of data and just calls function delegate call. And what function delegate calls, it calls target, which in this case is this address, with the data. So the multi-call was quite popular some time ago because it allowed you to call whatever function in generic way, because by using delegate call, you are preserving the message sender and value from the calling call. So this was super simple way of providing user possibility to perform multiple actions at once. Okay, we go into delegate call. So you can see here the raw data that finally was sent here. If we check raw data, we have function selector for burn, 4 bytes. Then we have 32 bytes of the amount that is to be burned. But you can see that additionally, we have these 20 bytes. And what are those 20 bytes? It looks like address, and you can see, for example, here that this is the address of Uniswap v2 pool. So this would not be a problem normally, but you can see that it's not uses message.sender, but it uses this overridden message sender. Okay, so we know that it passes the amount that it wants to burn. We know that it's like Uniswap v2 pool address, that is additional 20 bytes. And now let's see how the message sender function is being called. And you can see that this is this ERC context upgradable message sender. If we go inside, we can see our old friend. If this is trusted forwarder, which it is in this case, you take last 20 bytes. So this is the root of the problem. Because we were using multi-call, we could pass any arbitrary data to the function and strip off the initial message sender. And here we can override additional message sender through multi-call. But this is not the end. Of course, the burn succeeds. And now you can see that the function sync is called. So we are just syncing balance of token 0 and token 1 with the reserves. Why are we using that? Because we burned all the time token that the contract had in itself. Now the other side, the wrapped Ethereum part of the pool, we have a lot of it, and we have like I think that at this moment everything was burned from the pool concerning time tokens. So first the attacker took 5 WEF to exchange it for some time token, and he has some of it. Then he burns the token from the pool, and now look what happens. We have a lot of WEF and very small amount of tokens. So that means that the pool thinks that the time token is super valuable because, well, it has, like, if it has 0 of it and all the WEF on the other end, if you provide like 100 of it, that means that this 100 time tokens, for example, has super big value, and you are actually able to drain the other side of the pool this way. So let's see what happened next. We are syncing it, and you can see that we are doing the opposite swap right now. So we are putting this amount of our 4B token, which is our time token, and we want back our wrapped Ethereum. Then we check our balance off, and you can see that the exploiter was able to get, for this amount of time token he provided, he was able to basically drain whole pool and receive 94.5 Ether. And now this is super easy. Now we are just calling withdraw and we have the money. And this is how the attack took place. So how can we provide this issue? Like, first of all, I believe that we have some bigger problem with ERCs and EIPs. And in my personal opinion, the problem is that people are having good intention and good ideas how to improve Ethereum and provide some new standards for everyone to follow. However, they're not really taking security into consideration when they are doing that. And this is the core of the problem. Just imagine, in case that, you know, 2 independent security researchers with decent knowledge of Web3 security look at that, they would right away disallow this EIP. Because just look, you know, at how you can manipulate that just by the fact of how Solidity works, that you can actually append any calldata that you want. And in this case, it was used to burn all of the balance of Uniswap v2 pool. Apart from that, if you are not knowing what you're doing, you should better not do it. And for the most part, the message sender should not be used unless you are really confident that you know what you're doing. In this case, I don't think the team were aware of possible issues with the additional multi-call that they had, because if not for the multi-call, the attack would not be possible, because the trusted forwarder already appended the message sender to the end of the call data. So it was only possible through the usage of multi-call. So actually this is very old problem, very old vulnerability, but rediscovered with additional factor of multi-call. So yeah, that's all for today. I hope you learned something new, and see you in the next one.